In this video, we'll be talking about the domain of rational functions. Now, by a rational function, we really mean a fraction formed by polynomials. That is, some n of x over d of x, where n and d are both polynomials. Here, n stands for numerator, so the numerator polynomial, and d stands for denominator, the denominator polynomial. Furthermore, the domain of a rational function is actually exactly what you would expect it to be. Namely, all real numbers except x values that make the denominator equal to 0. So for example, let's go ahead and find the domain of the function 1 over x and discuss what sort of behavior, what its behavior is at that at any excluded x values, and then you'll do the same thing with the function f of x equal 3x over x minus 1. So first off, 1 over x, the domain is simple. It's just x, it's the set of all x where x does not equal 0. So, or if you prefer interval notation, negative 0, union 0 to infinity, because we skip over 0, right? A natural question then is what sort of happens close to 0? Well, if we make a table of values, it's not too hard to sort of see here of what's happening. So let's look at some x values, and then we look at f of x as well. Well, the question is sort of what happens at 0, right? Well, let's take values from either side and see what happens, right? Well, here, if you look at x equal negative 1, on negative 1, what happens is we have negative 1 gives us back 1 over negative 1, which is negative 1. If we plug in negative 1/2, we end up with, or negative 0.5 if you really just love decimals. Negative 0.5, you'll get negative 2, because 1 over 1/2 is 2. If you plug in negative 0.1, you'll get negative 10. If you plug in negative 0.01, getting really close to 0, you'll get negative 100. So here it's interesting because it looks like it's getting really, really negative. Namely, what we say is that f is kind of going to negative infinity because it's getting so negative. On the flip side, if we look at 1, we get 1, but plugging 1 in, we get 1. Plugging 0.5 in, we get 2. Plugging 0.1 in, you get 10. And plugging 0.01 in, you get 100. So here it's getting really, really high, and so it's getting really, really big in the positive direction, so positive infinity. This isn't too hard to see, though, if you think about the graph, which this is one of those graphs you should have memorized. If this is 1, and this is 2, etc., 1, 2, 1, 2, we know the graph looks like this, and these values kind of help you see that. There and there. But what we see is that, and we've seen if you zoom out, this actually goes really, really high, never quite hits 0. This goes really, really low, but never quite hits 0. Okay? So now let's have you try an example. Go ahead and try a similar logic with this problem. On the count of 3, I'll reveal the solution. 1, 2, 3. So here, x cannot be 1 because that's what makes the denominator 0, or if you prefer negative infinity to 1, union 1 to infinity. Looking at this, it's picking some values. It's not too hard to see, and you could pick even more values to get even closer to 1 if you prefer, that the graph is going to get really, really large in the positive direction as x approaches 1 from the right side, but if you approach from the left side, you'll get 0, negative 3, and negative 27. In other words, it's kind of going further down, right? So that's negative infinity. Sorry, I messed that up. Negative infinity, so it's getting large in the negative direction. For a bit more practice and working with the domain of rational functions, be sure to see page 175 and work problems 1 and 5 through 8 in the textbook. And in our next video, we'll go further into understanding rational functions by looking at vertical and horizontal asymptotes.